大家好，这里是投资快讯，在这里您能了解到能源科技类的最新资讯。过去的3年多来，投资快讯小编一直关注的核能板块，在清洁能源、电动汽车、生成式 AI 的带动下涨了不少。不少人搞不清楚小型模块化反应炉 SMR 跟传统的核反应炉有什么区别。相信有不少人跟小编一样，稀里糊涂在油管大 V 的推荐下买了几股 Oklo。今天小编到该公司官网看了下，发现他们的技术其实都基于一个叫做 EBR2 的 SMR 原型机，据说已经安全运行了30年。今天小编找到了一个美国阿贡国家实验室拍摄的关于 EBR2 的纪录片，配好了中英文字幕，分享给大家，希望能对您的投资有所帮助。
Silent, unchanging, aloof. This is the land of the central Idaho desert. 100 years ago, pioneers crossed this land, forging westward on the Oregon Trail. It was here that the bad men of the Old West ambushed shipments of gold from the mines to the north. Even today, plunder worth many thousands of dollars lies hidden forever in the silent reaches of the desert and the lava beds that cross it. It was from these buttes, once active volcanoes in the prehistoric days of this land, that lava spewed forth to cover a large part of central Idaho. But it's wealth of another kind that has made the lava beds famous. Here in 1949, the Atomic Energy Commission established the National Reactor Testing Station, some 875 square miles, 3/4 the size of Rhode Island. It serves as America's proving ground for nuclear power. Today, caravans of buses and cars retrace the tracks of those covered wagons of yesterday, bringing to the site scientists, engineers, and technicians from Idaho Falls and some 30 other neighboring communities. Among many firsts, these were the people first to light a bulb and later a town with atomic power. These were the people who revolutionized naval power with the development of the nuclear submarine. And today, these are the people developing the atomic power plant of the future, as they continue to answer the challenge of the atomic age. Challenge is produced through a grant from the United States Atomic Energy Commission's Argonne National Laboratory. This is the control console of the experimental breeder reactor number 2. Here, isolated on this Idaho desert, is one of the most advanced and complex atomic power facilities in the world. From this nerve center of EBR2, as it's called, scientists and technicians monitor the intricate processes of nuclear fission and gather information that will guarantee a plentiful supply of atomic power for the nation and the world for centuries to come. This reactor is different in many ways from the nuclear power plants that supply some of our homes today with electricity. It's unique because it creates more atomic fuel than it uses. Dr. Harry Monson, the project manager for EBR2, can tell us how this is possible.
This reactor actually does create more fuel than it uses, Norman. That is not to say, however, that it's a perpetual motion machine. We still can't create something from nothing. Basically, with EBR2, we are developing methods of extending our nuclear fuel reserves. We do this by converting an inert material not usable as a fuel to plutonium, which is a man-made nuclear fuel well suited for use in power reactors such as this one.
That sounds like a complicated process.
It is complicated, and the equipment required is complicated. Yet, if we are going to utilize all the nuclear fuel reserves our country possesses, we're going to have to build many large plants of this general type to make plutonium. The reason is this. Uranium, as it occurs naturally, as it is mined, consists principally of a mixture of two kinds of atoms. One is called uranium-235, the other uranium-238. Less than 1% of the mixture is uranium-235. Yet, this small amount is used to supply almost all of our conventional atomic power. The bulk of the mixture, on the other hand, is uranium-238, which is not usable as a fuel unless it is first converted to plutonium. Unless we convert 238 to plutonium in this way, we will waste most of our nuclear fuel reserves.
Would you say that using the 235 and not the rest is sort of like using the cream and throwing away the milk?
Exactly. This reactor saves the uranium-238 by converting it to plutonium through a process called breeding. By this process, we create more fuel than we use, and in so doing, consume the uranium-238, which, except for the benefit of this process, would be practically worthless to us.
How is breeding accomplished then?
Well, let me show you here. This is a model of a large tank we call the EBR2 primary tank. It is 26 feet across, some 26 feet in height. The tank is almost completely filled with a molten metal, sodium. Submerged in the sodium near the bottom of the tank is the reactor. At the center is the core, or nuclear heart, of the reactor. Within this core, the neutrons, which you'll recall are particles from the nucleus of the atom, cause the fission reactions which yield the heat we use to produce power. This reactor is so designed that the number of neutrons present is greater than the number required just to sustain the chain reaction and produce the desired heat. We use these excess neutrons to convert uranium-238 to plutonium. Some of the uranium-238 is placed in the core of the reactor. Most of it is located in the so-called breeding blankets surrounding the core.
It all sounds fairly simple, but I suppose it's far from it.
Well, the basic difference between this reactor and the conventional atomic power reactors lies in the speed of the neutrons employed. This reactor uses very fast neutrons. In designing a reactor to use such fast neutrons, however, a number of difficult problems are encountered. Perhaps you'd like to see how some of these problems have been solved. Reactor plant permissive, please. Ross and Monson. Thank you. We'll each have to carry a radiation dosimeter, Norman.
These heavy doors look as though they belong in a submarine.
You'll see doors like this at many of the atomic power plants. Our reactor, and indeed the entire reactor building, are totally enclosed within a heavy steel containment shell. To get into that shell, we have to pass through this double-doored airlock.
You mentioned fast neutrons a moment ago, Harry. What are they?
They're truly just that. They're fast. When the neutrons first are born in the fission process, they are highly energetic. They have great speed. As they move about, however, they start to collide with various atoms of the reactor. These could be atoms of fuel or of structural material or of coolant. With each collision, they lose a fraction of their energy. They tend to slow down. In this reactor, we wish to keep the neutrons fast to enhance the breeding effect. One of the principal reasons we use sodium as the coolant is that as neutrons move through sodium, they do not lose their energy as quickly. They don't slow down as rapidly as they do in the more ordinary coolants, such as water, for example. In fact, we submerge the entire reactor in sodium in the big primary tank. The tank contains about 90,000 gallons of sodium, or 320 tons. Incidentally, it took 10 railway tank cars to bring the needed sodium to the EBR2 site. The bottom of the primary tank is about 40 feet below floor level in this building. Here in the sub-basement of the building, you can see on the right the outer surface of the heavy concrete radiation shield, which completely surrounds the primary tank. The air ducts you see are used to carry cooling air to the shield. The cooling is needed to remove the heat generated in the shield by absorption of neutrons and gamma rays from the primary tank. Because of this radiation shield, we cannot see any part of the primary tank itself. And of course, we can see nothing inside it. To accomplish the necessary operations inside the tank and to keep in touch with what is going on there, many special mechanisms and instruments are used. Now we are approaching the operating floor. Above the operating floor, you will be able to see the tops of some of the many mechanisms used for controlling the reactor and for handling reactor fuel down inside the primary tank. These are the control rod drive mechanisms, Norman. They raise the control rods to start the reactor and lower them to shut it down. Over here is the top portion of one of the mechanisms used for changing fuel in the reactor.
That must be quite a formidable task when you can't even see what you're doing.
It is, but we're able to control almost the entire operation from this computer console here on our left. Before attempting to describe the fuel changing procedure, let's again look at this model of the primary tank. We are standing here on the operating floor level. Directly underneath us is the primary tank. The cover of the primary tank is particularly interesting. It has about 70 penetrations or holes for insertions of mechanisms. The details of the cover are not visible on this model, but we can look at a few photographs taken during construction. The cover was made in two halves. This is a top view of one of the halves during fabrication. Many of the holes or nozzles, as they are called, can be seen. Here, the two covers have been assembled. This is the bottom of the cover. Again, many of the holes through the cover can be seen. Later, each hole was fitted with a plug carrying a mechanism or an instrument. With all the plugs in place, the cover is completely gas-tight. Note in particular this large central hole. It is 12 feet in diameter and is fitted with a plug weighing 120 tons, which is rotatable as well as gas-tight. Within that plug is a smaller rotating plug. Here, the almost completed primary tank is being lowered into its cavity in the operating floor. Inside the primary tank, down near the bottom, is the reactor. The reactor, too, is fitted with a cover. That cover can be raised and lowered to provide access to the reactor. The reactor consists of a cluster of long, thin assemblies containing fuel. This is a model of such an assembly. Only the central portion of the assembly contains fuel, uranium-235 or plutonium. The upper section and the lower section both contain uranium-238 to be converted to plutonium. To insert an assembly with new fuel into the reactor, the following procedure is followed. The assembly first is loaded into the fuel loading machine, some of the controls for which can be seen at the top of the machine and the others on this console on the floor. The machine then is brought to this end of its track, and the assembly is lowered out of the fuel loading machine down through this transfer port into the primary tank. At that time, this mechanism we noted earlier takes the assembly and swings it to a position in the primary tank called the transfer port. Then the two rotating plugs rotate, and a gripper mounted on one of the plugs is positioned directly over the assembly. The gripper is lowered and takes the assembly from the transfer arm. After another rotation, the assembly is lowered directly into the desired position in the reactor.
How often must you change the fuel?
Well, this depends upon the power level at which the reactor is operated. Not all the fuel is changed at one time. 2, 3, or perhaps 4 assemblies at a time. With the fuel in the reactor, as it is undergoing burn-up by fissioning, fission products are retained. Accumulation of these fission products result in distortion and weakening of the fuel. Eventually, they cause the necessity of removing the fuel. When the fuel is removed, it is not taken out of the primary tank, however. Again, if I may use the model, the assembly is placed in this storage basket. There it stays until the decay heat generated within the fuel has subsided. This takes about 2 weeks. Finally, the fuel is removed from the storage basket, taken out of the primary tank, and is ready for reprocessing.
Just building the equipment must have been nearly a superhuman task, I should think. You said a little while ago that a breeder reactor is a complex instrument. I'm beginning to think that that's a major understatement of the year.
Well, practically all the mechanisms and equipment you've seen in this building have had to be designed and built specifically for this reactor.
That's really fascinating. I'm just sorry that time doesn't permit us to see more than that, but we do have to move on. We now will show you how all this fits together. To do that, we'll retrace our steps to the control room in the power plant.
You might wonder why our control room and this turbine generator are located in a different building hundreds of feet from the reactor itself. The reason is that we deliberately confined the reactor and all other intensely radioactive portions of the plant to one small area, and then built a steel containment shell totally enclosing that area. These portions of the plant do not involve any radioactivity, and therefore we were able to place them in these much more convenient locations. Here in the control room, I believe I can give you a general idea of how the entire plant functions. The power cycle of EBR2 consists of 3 heat transfer systems: the primary, secondary, and steam electric systems. This graphic panel illustrates the flow paths of these systems. In this area, the primary system is represented. The major components are the primary tank, outlined here, the main heat exchanger, 2 sodium pumps, such as this one, and the reactor itself. In the core of the reactor, an enormous amount of heat is generated within a very small volume. If that heat were not removed as rapidly as generated, the reactor would melt. To remove the heat, we pump some 9,000 gallons of sodium through the reactor every minute.
What would happen if the pump suddenly failed?
The reactor would shut itself down immediately, automatically.
I see.
In the adjacent area of the panel, the secondary system is shown. The sodium flows from the secondary pump through the main heat exchanger, picking up from the primary system the heat it had picked up from the reactor, and then flows over to the steam generator in the sodium boiler plant.
What a fantastic arrangement of pipes.
It is. Basically, it's just another series of heat exchangers. However, these exchangers are of highly refined, very sophisticated design. In these units, the heat is transferred from the secondary system sodium to water to generate steam at a temperature of about 840 degrees Fahrenheit and a pressure of 1,300 pounds per square inch. The steam then flows to the turbine generator located just outside the control room. The flow paths of the steam system are shown in this portion of the graphic panel. There are too many small flow paths for us to be able to follow them through.
This control room is such an amazingly complicated looking place. Is the operation as complicated as it looks?
It is relatively complex. We do use a great deal of automation, however, to aid us. As one example, we even use a computer to read many of our control instruments for us, and automatic typewriters, such as this one, to record the information. Nevertheless, it is necessary for our operators to maintain a very close watch over a number of the more important instruments.
Shall we take a closer look at some of those instruments?
Yes, let's start over here. Our control panel is divided into sections. Each section corresponds to a particular part of the system. In this section, monitors keep track of the radioactivity levels throughout the plant. You'll find that each section has its own alarm system to tell the operators when something is amiss. When that buzzer sounded, this light went on, indicating that the shield cooling system flow rate was too low. The operator acknowledged the alarm by pressing the silencing button. He'll now investigate the cause of the low flow. The next section relates to the secondary system. Here, various temperatures, pressures, and flow rates of that system are monitored. This section pertains to the primary system. Here, hundreds of temperature, liquid levels, pump speeds, and the like are indicated and recorded on these instruments. Now we come to the nuclear panel. Here, the neutronics of the reactor are monitored. This is the panel that the operators watch most closely.
What are these dials? These look like giant temperature gauges.
These are control rod position indicators, Norman. There are 12 control rods and 2 safety rods. The height of the tape indicates the amount by which the particular rod has been inserted in the reactor. In this case, for control rod number 8, the rod is in some 11 inches. The digital indicator underneath shows the rod to be in precisely 11 4/4 inches. These instruments record the neutron flux levels in the reactor. Next comes the large graphic panel at which we looked earlier.
I remember.
And beyond it are several panel sections which relate to the turbine generator and the electrical power distribution system. These are quite conventional. They're about the same as you'd see in any steam electric power plant.
How much electric power do you make?
About 20 million watts, Norman. That's more than enough to power a city of, say, 25,000 people. As you know, however, the production of power is not our prime objective. In EBR2, we are collecting data and information with which we can design very large power breeder reactors to power our large cities in the future.
I see. One aspect of this system is perhaps more revolutionary than anything we've seen so far. This reactor is the first in the world to have its own fuel processing plant attached to it. This plant is completely integrated. It's tied right into the reactor system. We have time for just a very brief look at it.
When a used fuel assembly is removed from the primary tank, it is taken out of the reactor plant through an underground airlock into this building. The assembly is transported in a heavy shielded container called a coffin. Here we see a dolly moving the coffin up to this open hatch. The coffin next will be lowered through the hatch to another dolly, which will move it into position underneath the air cell directly ahead of us. A manipulator will pull the assembly out of the coffin up into the air cell. A remotely operated machine then will disassemble the unit to obtain the 91 fuel elements it contains. This is what the fuel elements look like, Norman. All 91 elements then are passed through an airlock into the argon cell. Here the fuel elements are entering the argon cell, which has an atmosphere of pure argon to minimize corrosion of the fuel alloy during reprocessing. At this first station of the argon cell, a remotely operated machine is used to strip this thin stainless steel jacket off the fuel alloy and break the fuel alloy into small pieces. In the next step, the fission products are removed from the fuel alloy by a process called melt refining.
What is melt refining?
In this process, the pieces of alloy are placed in a crucible and melted. At the high temperature employed, some of the fission products are driven off as gases and vapors. Most, however, react with oxygen of the crucible to form a slag or dross at the top of the melt. We pour the purified metal right out from underneath the dross to form an ingot like this.
Oh, it's a heavy one.
Uranium is heavy. That clean metal then can be used to fabricate new fuel pins. We use a technique called injection casting. At this station is the injection casting furnace. After casting, each of the pins is inspected for weight, length, diameter, and volume.
You know, I'm amazed at the complexity and also the variety of your different instruments. Now, that looks to me exactly like a periscope.
That is a periscope. We use that to obtain close-up views of items inside the cell when necessary. After inspection, each pin is inserted into a thin stainless steel jacket in this manner. A small amount of sodium is added to provide a thermal bond between the fuel pin and the steel jacket. Then, using the sodium settling furnace, we melt the sodium and uniformly distribute it throughout the fuel element. Finally, an end closure is added and welded. That completes the fuel element. New fuel elements such as this are identical to the used fuel elements originally brought into the building, except, of course, minus the fission products. These new fuel elements are transferred from the argon cell back to the air cell. Here, an enormously complicated, remotely manipulated machine places 91 fuel elements on the grid structure of a new fuel assembly. Later, the blanket sections are added and the stainless steel outer can slipped over the assembly. This completed fuel assembly finally is removed from the air cell, placed in the coffin, taken back to the reactor plant, and inserted in the reactor, thus completing the fuel cycle.
Thank you very much, Dr. Munson. This has really been a very fascinating tour. In this past half hour, we've had just a very brief look at the future of atomic power. And this, of course, is just the beginning. As a special Atomic Energy Commission report that was prepared for the President back in 1962 said, breeder reactors will enable us to use all of our available nuclear resources in the making of fuel. The future value of a given amount of uranium can be multiplied by much more than 100 times. And this fact makes our reserves almost limitless, because we have vast deposits of low-grade uranium ore. After all, every piece of granite contains some uranium. With the development of the breeder reactor, we can now begin to see that nuclear energy is economically reasonable and that it can be produced on a massive scale. As a matter of fact, nuclear power has already become competitive with conventional plants in some parts of the country. And by the year 2000, more than half the electric power of the country will come from atomic sources. We have indeed just begun. Said Thomas Alva Edison back in 1921, and that was some 20 years before the advent of the atomic age. Not only will atomic power be released, but someday we will harness the rise and fall of the tides and imprison the rays of the sun.
节目最后，如果本期资讯对你有所帮助，请您点赞、评论、订阅并打开小铃铛，这样您就不会错过本频道的最新内容。谢谢。